Okay, so the zeros are quadratic. Let's say we had a quadratic equation that looks something like this. Then what we can do is we can factorize this. So if we take a factor of xa out, and then we can make this a factor of the zeros, where alpha and beta are zeros of p of x, okay? So we know how to do this. So a good example of this would be, let's say we had p of x is equal to 2x squared plus 4x plus 3, then, 8x plus 6, something like this, okay? Then we can take a factor of 2 out, which leaves us with x squared plus 4x plus 3, and then we can factorize the inside by doing a factor of the zeros, in this case, which is 3m1. So by doing this with the original generalized equation up above, so up here, if we take p of x, which is equal to a lots of x minus alpha, and x minus beta, if we were to expand this, you guys should remember that what we end up with is a lots of x squared times minus x beta minus x alpha plus alpha beta. Okay, so this is just expanding this line out here. And what happens is you get a combination of both adding and subtracting, adding and multiplying the zeros, okay? So in this case, we have what we call the sum of the zeros, okay? Because if we essentially take our factored form and multiply it out, the x coefficient, or the coefficient of x, is just the sum of what the zeros of the original polynomial are. And here, the constant term is the product of the zeros. So it's essentially the product of the zeros of the equation, okay? So expanding this out one last little bit, we get a lots of x squared minus a lots of alpha plus beta x plus a lots of alpha beta. Now this is really, really powerful because it actually allows us to come up with equations for the sums and products of roots, which allows us to actually find the sums and products of roots later on. So if we were to actually look at this, we could say, well, back at our original equation, our term in front of the x is called b. So b, in this case, in this equation, is actually equal to minus a lots of alpha plus beta. Okay, so the coefficient of b is equal to minus a, which is the leading coefficient, lots of the sum of the roots. Or in other words, the sum of the roots is equal to minus b on a, which is the sum of the zeros. I keep saying roots, it's the sum of the zeros because it's only polynomial. Okay, alternatively, we can say the same thing about the product. Okay, so this end term here is equal to, well, our last little section up here, which is our c. So what we can do is we can actually calculate c is equal to a lots of alpha beta. So the product of the roots is just equal to c over a, which is the product. And this is actually going to allow us to work out what the zeros are without having to do any division or anything like that. So let's have a look at an example of exactly this. So starting off with, show by substitution that x is equal to 5 is a zero of the polynomial 3x squared minus 30x plus 75. So what we're going to do is we're going to take this polynomial, p of x is equal to 3x squared minus 30x plus 75. And what we're going to do is we're going to substitute 5 into this equation. We're going to get 3 lots of 5 squared minus 30 lots of 5. 30 lots of 5 plus 75. Okay, and if we put this into our calculator, we get 3 lots of 5 squared. Okay, minus 30 lots of 5 plus 75, okay, which is equal to 0. So, with that being said, that must mean that x equal to 5 is a 0 of p of x. Now, the sums and the roots, some of the roots or some of the zeros and the product of the zeros are two ways to find out other zeros of a polynomial. And these ones are a bit better than our remainder and factor theorem because they also allow us to find any doubles. So the remainder and factor theorem also helped us find zeros of polynomials, but they didn't help us find different, or if any of the roots were actually double roots or triple roots, etc. So what this allows us to do is exactly that. We can actually find if we have any double or triple roots. So our next part of the question is use the sum of the zeros to find the other zero. So in other words, what we're asking is we want to show that minus b on a is equal to alpha plus beta. Because if we go back to that previous page, we were saying that the alpha plus beta, the sum of the roots, is just the same as if I took the negative of this term out the front and divided it by this one here. And so let's do that exactly that. So we've got minus of minus 30 on 10, which is equal to alpha plus beta. So the sum of the roots, okay, has to be equal to 10. And I'm going to draw that 10 a little bit better. Okay, so you might be saying, well, why is this useful? Well, we already know what one of the zeros is due to part A. We know that x is equal to 5 is a 0. So what we can do is we can actually substitute that 0 in to this equation. And what it'll do is it'll allow us to work out what the second root is. Oh, that should be a 5, not a beta. So once we make that substitution, we rearrange for alpha, and we get that alpha is also equal to 5. So therefore, alpha equals to 5 is a double root, or double zero, of p of x, okay? And so what you could do is you could substitute it back into this equation here to get the value back out. Or alternatively, you could divide by x minus 5 times x minus 5 and get that the remainder for this particular polynomial is equal to 0. Now part C says use the product of zeros to find the other zero. So essentially we're going to be coming up with this answer here again, but we're effectively using the fact that, we're using the fact that we can use either one of these rules to work out what the second root is. So for part 3, that is, we have we have the sum of the product of the roots is equal to C on A. So that is the constant term divided by the leading coefficient. So in this case, it's 75 divided by 3. So what we're going to do is we're going to rewrite this as alpha beta is equal to, and I can even write over here, C is equal to 75, A is equal to 3. So 75 on 3, so the sum of the product of the roots, I should say, is equal to 25. Now again, we know that one of the roots due to part A, okay, one of the zeros due to part A is equal to 5. So what we're going to do is not let x be equal to 5, we're actually going to let beta be equal to 5 again, just like we did before. And so when we do that, what we get is we get 5 alpha is equal to 25. So in that case, alpha must be equal to 5. So just like we had before. So essentially, what this is doing is demonstrating that it doesn't matter which method you use. If you already have one of the zeros, you can actually calculate the other one by doing the sum or the product. Now, part B, well, that should say part 2, not part B there. Naughty, naughty. Now, part B says find the sum of the zeros of this quadratic here, and hence find its axis of symmetry. Okay, so the sum of the zeros is very useful for this question. So what we're going to do is we're going to rewrite this polynomial out again, so I don't have to keep scrolling back up. So it's equal to x squared plus 7x minus 11. Okay. So we know that the sum of the roots is equal to negative b on a. So a in this case is equal to 1, b is equal to 7, and c is equal to minus 11. So we've got our three values here, because remember, a is that term, b is that term, c is that term. Okay, and what we can do is we can substitute them straight in. So alpha plus beta is equal to minus 7 on 1. So that means that the sum of the roots is equal to minus 7. Now you might be thinking to yourself, well, why is this actually useful? Like, we don't really care, or we can work out that that's equal to minus 7, like that's one of the zeros are. Why is that useful at all? Well, it's useful because what we can do is we can actually use it to work out or calculate what the axis of symmetry is, which is the second part of the question. So if we go back up, it says, so find the sum of zeros. Okay, well, we've done that. It's minus 7, and hence find the axis of symmetry. So if we think about the picture of a quadratic equation, which is a very poorly drawn on my behalf, and I'll make it the simple one because it works for all of them. The quadratic equation creates a parabola, okay? And I've actually changed my mind. I don't want to do that one. I want to do a different one. And my different one's going to go like this and not like that because that's really bad. It's going to go like this. Okay. So it's really, really obvious where the axis of symmetry is for this particular object. And it should be, or you should notice that it's going straight down the middle. So if you recall, to find the axis of symmetry, what we do is we just find the average of the two roots, or the two zeros. So the axis of symmetry, in this particular case, if one of my zeros is alpha and the other one is beta, would be alpha plus beta on 2. Well, on the left-hand side, we've actually already calculated this top section here. And we've done that over here with the sum of the roots, which is minus 7. So that means that we can calculate the axis of symmetry by just using that, the alpha plus beta. So it's alpha plus beta on 2, which is equal to minus 7 on 2, which is equal to negative 3.5 or negative 3.5, depending on your style. And that gives you your axis of symmetry. Now, you might recall that the axis of symmetry of a parabola can also be calculated using minus b over 2a, so which is the axis of sym. But if I was to break this up into 2 bits, it's the same as having minus b on a times a half. And minus b on a is just equal to alpha plus beta. And then the times a half, okay, is the same as having alpha plus beta on 2. And so there you go. That's how you can get your axis of symmetry in more than one way. So with that being said, that's the end of this part of the video. Okay, so the quadratic equation. What we're going to be doing next is going to be looking at the cubic equation and doing a similar sort of work for this one.